I'm Brady Hardiman. I'll be your Songlin today. For those of you that don't know me, I'm an associate professor in Forestry and Natural Resources. I have a joint appointment in environmental and ecological engineering, and a member of Digital Forestry. I'm going to introduce our speaker today, but first I wanted to show the upcoming seminars. We've got 5 more remaining through the semester, so make sure those are on your calendar. Lots of good things to talk about and learn about. Today, we're very fortunate to have Dr. Jim Garrison with us. Jim is a professor in the School of Aeronautics and Astronautics here at Purdue. He got a Bachelor's of Science from Rensselaer Polytechnic Institute, a Master's from Stanford, and a PhD from UC Boulder. He's been doing some really interesting work, and I was learning more about it this morning. Jim and I worked on a couple of proposals together, but it's always fun to look at somebody's Google Scholar page and think about their whole body of work. And so Jim's research focuses on using signals of opportunity to remotely sense the Earth's surface. So signals of opportunity, he'll tell us all about what that is, but it's a new technique and a new way of measuring the Earth's surface in ways that hadn't previously been thought about. And so Jim is the leader and the founder of that approach. So his previous projects have focused on measuring soil moisture, biomass, and surface winds or ocean surface winds, just to name a few. He's the lead PI in the NASA SNOOPI mission, which he'll tell us about today, which should be launching soon. He's going to demonstrate new approaches to more accurately measure soil moisture and improve estimates of stream flow, crop yield, forest carbon storage, and many other aspects of global climate. His research accomplishments over the years were recognized in 2022 with his election as a university faculty scholar, and he has numerous other accolades, too numerous to mention. So we're very fortunate to have Jim here today. Jim can go ahead and get started, and I'll just say one other thing, which is that the digital forestry seedling proposals are due March 1st. Carl either just did or was about to send an email, so heads up on that. Jim, take it away.
All right, thank you very much. As I said, I'm going to talk about remote sensing using signals of opportunity. The second part, we always have our standard presentation slides that we give everywhere, and we just kind of mix things together, move a few things around. So applications are going to be part of it. I'm going to talk a lot about the principle of the technique as well before we get to application. So it's maybe a little weak on applications compared to what the title suggests. But I'm going to talk about new technique of remote sensing that I think has some applications in agriculture and forestry and various forms of land remote sensing. So to start with, introduce what is signals of opportunity, and kind of before that, I'm going to introduce kind of where the scope of remote sensing that fits into, because when I say remote sensing, or I look at conferences in remote sensing, I mean it really spans a very wide range of fields, from people using GIS for socioeconomic modeling to very physics-based electromagnetic scattering theory and stuff like that. So I'm going to kind of scope down what I'm talking about when I say remote sensing, and then I'm going to talk about some basic principles, and the specific technique I'm going to talk about is the use of what's called P-band, which if you talk to communications engineer, they'll say that's UHF and VHF, but to a scientist, we call it P-band. And what's the unique properties of P-band sensing for these types of land remote sensing, specifically soil moisture, vegetation, forestry, and stuff like that. And I'm going to then talk about some simulation studies we've done to look at this measurement and look at some requirements for, this was funded under NASA grants, so look at some requirements for a future mission, but also look at the sensitivities to measuring root zone soil moisture and above ground biomass. These are supported by some experiments, and then I'm just going to talk about the technology that I'm involved in to bring these things to practice. Okay, so introduce remote sensing. This is a slide I use in many of my classes, and I always make the disclaimer, this came from an astronomy website, so everything is backwards from the way I think of it. First of all, everything's a wavelength and not frequency, so be careful if I say bigger or smaller, I might have those two reversed. And also this shows, us on the ground looking out, but of course, remote sensing, we are in space or in the air and then looking down at the ground. Okay, so the Earth's atmosphere is largely opaque, 100% opacity, so it blocks most of the electromagnetic radiation from both the very long wave and the very short wave. So we're not exposed to gamma rays or anything like that. But there's two small windows that the Earth's atmosphere is somewhat transparent. The optical window here, which is why we can see the stars at night, and the microwave window up here, which is where radio astronomy operates. And that's the realm I work in. The one thing you'll notice when you look at this plot is even though the optical window I said is transparent, it's got that really complicated response there. And of course, that's going to change with weather conditions and all kinds of things. So the good advantage of microwaves is it's almost completely transparent. So microwaves have much less of a sensitivity to what the atmosphere is doing. Okay, so classical techniques of microwave remote sensing that have been around probably in some way since the Second World War, largely developed in maybe the 60s or 70s. One is passive radiometry, which makes use of the fact that anything that's not at absolute zero emits electromagnetic radiation. So I can capture that radiation and see how it's related to an emissivity at the surface and compare that with some lab measurements that relate emissivity, say, for example, to soil moisture, and I can get a way of taking this emissivity measurement and inverting it and getting soil moisture. Another classical technique is an active technique, a radar, what's called scatterometry, in which I use a human-generated pulse from my instrument, from my radar. I bounce it off a surface, and I measure scattering cross-section. A classical technique of this is in ocean remote sensing, where I can see a dependence of the backscatter on the direction of the wind or the direction of the waves. So that's a classical technique of active remote sensing. So what is signals of opportunity? Signals of opportunity is kind of a mix of both, but it has some properties that are unique that don't really fall into either one of those two categories. Signals of opportunity takes an existing non-cooperative transmitter, and I'm going to say an anthropogenic source, a artificial source. Now, in principle, I could maybe use an astronomical source, and there has been, I know of some work being done where they're using, say, the sun's illumination, but let's focus it on a non-cooperative transmitter. For most of my work, this was a navigation satellite because I began my career doing GNSS navigation, but we also look at communication satellites. So something that's transmitting a signal that we know some of the properties for. We don't need to know everything. We don't need to have any license to decode it or use it or anything like that, but we have something that's emitting electromagnetic radiation that we can figure out some of the properties. Well, some of that's going to scatter off the ground. Not the intended purpose. It's not getting to a dish in somebody's yard or anything. It's just reflecting from the ground. And in most cases, there's going to be a very small backscatter signal. But this is what the radar would be. So very small in most cases. In most cases, for most naturally occurring types of surfaces, I'm going to have a much stronger forward scatter. Following approximately Snell's law, angle of incidence is angle of reflection. Much stronger forward scatter. And then I can also compare that to a direct line of sight signal, because again, I don't need to know too much about the transmitted signal. Again, I don't need a license or anything to decode anything or anything like that, because I'm using that as a reference. And really what I'm looking at is the change in that signal as it scatters from some surface. Okay. And the things I can extract, and I often refer to this as the third way, it's neither passive nor active. And so some of the electromagnetic observables we can make is reflectivity, the phase, coherence. I'm just maybe say a little bit about coherence, what that actually means. And in general, we talk about something called the delayed Doppler map. We basically say how the signal is scattered in delay and Doppler frequencies. And then we have some models that relate these to geophysical parameters. I just listed some of the ones that myself and my colleagues have looked at, things like, the same things we talked about with active and passive remote sensing, like wind vectors, altimetry, soil moisture, how, whether areas are flooded, whether there's presence of sea ice, anything like that, using some basic physical models. Okay, so to illustrate kind of one of the ways I can make this measurement, I'm showing this in graphics here without any equations or anything to kind of get to the basic physical principle. So if I have a transmitter at infinity and my parallel rays incident on the surface, and I have the problem setup of a flat Earth and the receiver, low, maybe this could be a tower or an aircraft, so I can approximate as a flat Earth, but the principle is still the same from orbit. Perfectly flat surface, I have a mirror reflection, and there's going to be one ray path that goes from the transmitter to my receiver. Okay, so if this was a navigation signal, my receiver is not going to be able to tell any difference between that and my direct line of sight from the transmitter that's used when I do my navigation solution. Another way of expressing that mathematically is if I do my cross correlation between the direct signal and the reflected signal, I'm going to get a nice sharp peak. So for a GNSS receiver, a navigation receiver, it's all based on tracking that peak because that's going to give me my delay, my time of travel from my transmitter to my receiver. Okay. Of course, if I try to navigate with this, I'm going to get a really bad solution. It's going to tell me I'm the mirror below the surface of the Earth, but I don't really care about that. I care about what sensitivity it has to the roughness of the surface. Okay, so now as my surface gets rougher, I no longer have a specular reflection. I now have multiple ray paths getting to the receiver. Okay, so now if I do my cross correlation, I'm going to see I'm going to have a model that spreads out, and I'm going to have a trailing edge that starts getting wider, and it's asymmetric because I'm not getting any reflections arrive earlier than the specular point. I'm getting a lot that arrive later to first order. I get some that arrive a little bit later just because of variation in height, but that's a small effect. And then now, if it gets even rougher, I see it spreads out even further. Okay, because I have the same amount of energy incident, I can also look at the decrease in this peak. It's also going to give me a measure of the roughness as well. Okay. The other thing to have, okay, so the other thing that happens as I go from the top figure to the last figure is that as the surface gets rougher, again, I get this multitude of delays, this distribution of delays, and this is an effect that you're probably familiar with optically. In the first case, if I have a perfectly flat surface, I have a specular reflection, and here we can see an example of a sunset, and you see an image of the sun, mirror surface, and then this one is the classical picture that everyone shows that was at one of the first conferences in this field, where I have a rough surface, and you'll see that I don't see an image of the sun, but I just see some illuminated area. And also this little region in here is smoother because I think it'll shallower water. You'll see that since it's smoother, I see a smaller spread of the signal, smaller range of delays. Okay. If I write this all in equations, my received signal I can model as a form of the radar equation. I'm just going to go through what some of these terms mean kind of conceptually so we understand how the measurement comes out of it. Okay, what I actually generate in my receiver is called the delay Doppler map. So I show one dimension there in delay. If I look at the frequency component of that, I also have a dimension in Doppler, satellite and my receiver maybe is also moving, so I get some Doppler shift as well. And unlike a single delay, or I'll get a single Doppler shift, I also get a spread of Doppler. So inside my receiver, I generate this function of delay and Doppler in general, and it depends upon the contributions across the whole surface, so this intervals over the surface, but buried in here is a bistatic radar cross-section. So it's just like when we talk about radar, we talk about cross-section, and this is just a non-dimensional quantity that is a function of polarization, roughness, surface reflectivity, and it can vary over the surface. If this is a large surface, and from a satellite looking at, say, the ocean, this could be hundreds of kilometers are contributing to this measurement. The other things, I'm not going to spend a lot of time on them. I have something called the ambiguity function, which basically tells me my resolution in delay and Doppler. So when I do the signal processing, I can isolate little regions in delay and Doppler. And I have all these other things, just the radar equation, 1 over r squared loss from the transmitter, 1 over r squared loss from the receiver, gains, and all of that. Okay. So the two cases, the incoherent scatter, the coherent scatter and the diffuse scatter, coherent scatter of a single ray path. So I'm going to have my delay Doppler map is ultimately going to have look like a delta function. So I somewhere here I have a delta function up there. So I'm basically only seeing scattering in one direction. So basically then my measurement is just the reflectivity of the Fresnel coefficient. Okay, so and I'm looking at most land surfaces at the frequencies I'm working with are going to be coherent. So I'm going to see a basically just a reflectivity at the surface, how much energy goes into the surface and how much scatters from the surface. For rougher surfaces, which may not be that relevant to most land surfaces, I see something that depends upon the distribution of slopes on the surface. So in the case of, say, ocean scatter, we have a model for these this distribution expressed as a probability density function of a surface slope, how all these facets of the ocean surface are distributed. And again, the basic idea is that as I get further away from the speculative point, in order to see a glint on the surface, I need to have my facet aligned with this bisector vector. So each little facet has angle of incidence equals angle of reflection is the basic physical principle. Okay, so what does a delayed Doppler map look like? So I now would look at inside my receiver and I have delay. So those figures I showed earlier would be just one slice through here. So I go, it's asymmetric. I go from, noise up to in red, and then I have this long trailing tail. But then if I look at the Doppler dimension, it gets a little interesting because I have this kind of horseshoe shape. And it can be asymmetric depending on the velocity vector. The interesting thing is each point in this delayed Doppler map maps in a non-invertible way to the surface. So the specular point, P here, maps the single point on the surface. But if it gets weirder when I look at delays and Dopplers that are away from there, because one delay in Doppler, if I look here, I see my lines of constant delay are ellipses, my lines of constant Doppler are these, they're actually hyperbola, but zoomed in, they look like a straight line. And I see there's 2 points with the same delay and the same Doppler. So I don't have an invertible map. I have a single point on the surface map, two points on the surface mapped into a single point of the delayed Doppler map. Okay, so this is a similar problem you see in synthetic aperture radar, but they can get away with that by using a certain shape of the antenna gain. Since we're using non-cooperative transmitters, we're going to be really the geometry is constantly changing and it's a lot more complex. So it's not easy to get rid of that ambiguity. Okay. So the other thing I talked about, the incoherent and the coherent in the delayed Doppler map world, that's what this looks like. So coherent reflection, like we'll see from most land surfaces, we're going to see a peak that's concentrated in a small range of delay in Doppler, and I intentionally made with the same scale. So I see the ocean is going to have this spread over many delays, but at a much lower power. So one of the advantages of this coherent scatter is that I'm going to get a much stronger signal at the receiver. All right, so I can make these measurements with smaller antennas, and I also have a better resolution measurement as well. Okay, so what frequencies can we make measurements on? Well, it turns out this is the spectrum allocation chart, and I used what I call the real estate analogy. Is you might think of this as kind of like your deeds to your property, right? So it's very competitive. Everyone's competing to purchase spectrum so that they can launch their satellite and transmit their their entertainment to everybody. So it's it's a limited resource. You have to have a license. You have to have a deed to access it. There's small little parts of that are protected for science use. That's not what's shown in orange. What's not shown in red and yellow. What's shown in yellow is those that are allocated to communications and navigation. Very small parts of all this are protected for science use. That may be like something like a national park or something that's protected. So there's always competition to try to buy the protected land because you want to help something because there's a lot of money made. Okay, so let's look at the part that is not protected, shown in yellow. So these are all the bands from space to Earth. So some of this stuff is for terrestrial communications or airborne communication. Everything in yellow is a allocation for someone to transmit a signal from space, from a satellite to Earth, and they purchase their license or making the maximum use of that to make money off it. Probably some of these are for public uses, but And what we'll see is that they're spread out over a range of frequencies between, a few hundred megahertz here up to about the 30 gigahertz. This is the range of bands that I showed in my earlier talk that actually penetrate through the Earth's atmosphere. Okay. In terms of what is protected, the interesting thing is that there's nothing protected below about 1 gigahertz. Okay, so go below about 1 gigahertz, there's really no protection for scientific use. Right, but there are, a lot of commercial uses. Okay, so that brings us to P-band. Okay, so it's a real quick introduction on what signals opportunity are. Let's look at what frequencies will be useful for remote sensing of the soil. So this is and not a very sophisticated calculation. This is basically just a 2-layer model where it had a dielectric constant of the soil. And I plot the penetration depth versus frequency, okay, for 2 different soil moistures, either volumetric soil moisture, 5%, 30%. And so I look at the penetration depth and I see that in L band, which is, again, within this lowest frequency that we have protection. This is what SMAP, SMAP uses, SMOS, any of those microwave instruments. NISAR is also going to be L band. Okay, so we see, the penetration depth for, for wet soils, 5 centimeters or so. So really I'm sensing the top part of the soil. Okay, and what we would like to get is we would like to get deeper. We use the term root zone soil moisture. I've always used 1 meter for that. I don't know if there's a more precise definition of root zone soil moisture, but that's what we will be interested in terms of the full water content of what's absorbed by plants. Okay, so to get down to all the way down to 1 meter with at least with this example soil I use here, it's probably not possible, but I can get down to 20 to 30 centimeters if I go to lower frequencies. That gets into the realm of P-band. And if you look at this log scale, I think this is about 250 something megahertz, and this is 307 megahertz. Okay, so why don't we use P-band? I already mentioned one reason, right? There's really no spectrum allocation, and that has a few consequences. But beyond that, there's some physical reasons as well. In terms of the passive microwave remote sensing, that follows the same optical principles as an optical telescope would, that in order to get a certain resolution on the ground, I need a diameter that's going to grow proportionally with wavelength, right? So if I have the same requirement for a certain resolution, and I mean, you're familiar with like SMAP, the resolution for an end user's perspective is probably not very good. It's like 9 kilometers and they smooth it down to 36 kilometers. That's limited because of this reason, because of those wavelengths, you need, I think SMAP is a 6 meter dish, right? 6 meter antenna. Okay, so if I now go down to 1/5 of that wavelength, right, that diameter is going to grow 5 times to keep that same resolution. Okay, so that's why there really hasn't been a P-band instrument in space. Recently, there was a study. This was a science study from about 20 years ago that looked at 435 and 137 megahertz. This was for root zone soil moisture and biomass, 30 meter diameter. I mean, this is a big, expensive project to build and launch that. The Europeans, ESA, is launching the biomass mission. I think next year. It's also been in development for 10 years and hundreds of millions of euros. 12 meter diameter and antenna. So still big instruments in order to get this meet this resolution requirement. Okay, let's talk about spectrum allocation. Another problem with biomass is it's only permitted to operate in the red and yellow regions. It cannot collect measurements in North America or Europe because of potential interference with radars. Okay, so they made a science case that they don't need to make measurements in Europe and North America and still get useful science. Okay, but still somewhat limited. Okay, the last thing I want to talk about is what's called radio frequency interference. But the fact that other people are using these bands means there's a lot of signals being transmitted. And if I'm looking at a passive measurement, remember, I'm looking at measuring the thermal emission of a natural surface. And that is I don't know how many orders of magnitude weaker than any man-made transmitter. So any garage door opener or car, key fob for your car is going to be, much stronger than any naturally emitted radiation. So that means, it's really going to be hard to make these measurements in the presence of all of these other sources. This shows a spectrum capture at a radio astronomy site, and over, the P band, 225, 480 megahertz. And I circled these two peaks here because these are actually transmissions from a communication satellite. So when I first started looking at P band, I said, well, could we use the signals opportunity idea and actually use these transmissions or overwhelming anything else of these frequencies and use these to make a useful measurement. All right, and so that was my first big instrument development proposal. Actually, that's not true. This is my second instrument development proposal. This was the first big one with NASA. We had this idea of proposing a prototype instrument to demonstrate using these P-band signals from a geostationary transmitter for soil moisture remote sensing. So this is the antenna, so it's still relatively large. It took up one of the windows on this aircraft. We also have S-bands as well, but use these two antennas. We do some kind of beam steering with that. We demonstrated the measurement. This shows our flight pan. This was over the Little Washita watershed in Oklahoma, which is these are actually the instrumentation sites, I think. I think these are the recipient sites. And since the transmitter was in geostationary orbit, we're looking south, and we flew east and west with the antenna on one side of the aircraft, and we didn't collect any data on the way back. Okay, so we demonstrated this works. We still have all this data, and I just other than just showing it works, we really haven't gone and processed this data. So this actually would be a really good thing to have a student to really get into that and compare it with the surface truth. But we proved that this idea works, and we have these are the types of measurements we made. We calibrated going over this lake, so it's a really high reflection over the lake, and we can then use that as a calibrated measurement to get these reflectivity measurements over land. We could see some features. We could see strong reflections from rivers and small lakes. So we get an idea. We use this to kind of verify what our resolution was. This is roughly our approximation of our resolution on the ground. We did see some RFI, possibly from like air traffic control. So we switched the frequencies around. But basically, we proved that we could capture these signals, and we proved that we can make a measurement using signals of opportunity in a band that has not been that practically useful for remote sensing, but has a lot of potential because of the penetration depth. Okay, so with that, we wanted to look at what could be done with this. So I had a student under a finance grant, and we started looking at some simulation studies driven by actual data. So I don't know if I can go as far as calling this like an observation simulation experiment. Because we're actually taking real data to simulate this. But the basic idea is, okay, so we have one measurement that has, penetrates deep into the soil, but that's going to give it, that measurement by itself is going to give kind of this integrated average as a signal penetrates through multiple layers. We really would like to be able to invert that and get a profile of the soil moisture, well, not some integrated average. So that, of course, means you'll need multiple frequencies and they penetrate different depths, and we have some forward model that we can invert. Okay, so he started looking at this. We took 5 years of data from in situ soil moisture measurements at the I think it was the USCRN sites we used all throughout North America, different types of environments. And we used this electromagnetic scattering model. We didn't develop it. It came from Mississippi State University. But we looked at taking this electromagnetic scattering model and modeling soil moisture profile based upon the in situ data, vegetation model, scattering to different types of vegetation. And then we use that to generate synthetic measurements at different frequencies. And then we looked at our retrieval. Our retrieval, since we have to invert the model, our retrieval is a much simpler model where all the vegetation is modeled by an optical depth. Then we have these different layers of the soil moisture. This just kind of shows our generation of our synthetic data and our inversion. We simulated annealing for the inversion. And we did a study of many different combinations of frequencies, polarizations. Since we're using signals of opportunity, we don't have the freedom to choose, say, an angle of incidence or a lot of things related to geometry. So that's kind of a random variable in the whole process. So what we looked at is we looked at two configurations for the receiver. One will be in this will be like a space station orbit, 51 degrees, and the other one will be in the polar orbit. And then we looked at kind of the statistical distribution of these measurements, and then use kind of a Monte Carlo technique for just pick different hypothetical measurements for each one of these simulations. Okay, and then we traded off. You can see the different. Okay, first of all, here we have 4 different frequencies. A is the lowest, 137 megahertz, and B is L-band, 1575. That will be a GNSS signal. And then we look at combinations of 4, 3, and 2 frequency combinations, and we rank these based upon their accuracy. So this is the root mean square error of the soil moisture retrieval. And obviously, you expect as we add more frequencies, our error decreases. Then we also looked at how close the measurements have to be together, because we have all, they're coming from different sources. So we're not, we can't just, put everything in one instrument and control the angle of incidence, control the simultaneity of the measurements. We're randomly selecting them. And so we looked at a time frame up to 1 week between measurements, and that kind of gives an idea of what our sensitivity is to the dynamics of the process on the ground. Again, we didn't do any of the simulation of hydrology here because we're driving this thing with real measurements. Okay. And that's to look at polarization. So this will be single polarization, dual polarization. So I'm intuitive the result, right? If I add another polarization, I get better results, especially in estimating vegetation water content. So we get better at separating the water and the plants from the soil moisture. As we have a shorter time between observations, we get more accurate. And also as we add more frequencies, we get more accurate. So none of that was unexpected, but we actually put some numbers to the accuracies we were expecting to get. Okay, so with this in mind, we wanted to do some experiments. We did the airborne demonstration, which is much more of just a feasibility demonstration, although I think the data is pretty good. And again, I have a student, I'm kind of hoping that she can go and start getting into some of that as well. But we set up some experiments here at Purdue at the acre site to try to test some of these ideas and actually get some actual demonstrations of our ability to make these measurements. So we first set this up before everything shut down with the pandemic in 2017, and then we followed up in 2018. And this shows kind of our configuration. I'll show the tower on a later slide, but we have a portable tower. Maybe some of you've seen it when it's out there, and we can put some antennas on the tower and collect data. We have power, we have an internet connection, so we don't have to worry about anything you'll do if you're doing distant field work. And this kind of just shows, we set it up so that our P-band satellites cover this region in red. It's at geostation, it's at a geosynchronous orbit, but because it has a small inclination over the day, it slides a little bit over the ground. So within this box, and this just shows over 1 day's variation, and the ellipse shows our approximation of the resolution. There's also this S-band transmitter, which is what provides XM radio, and it's in a lower inclination orbit, so it is a little bit smaller Fresnel zone. And so we set up some hydro probes under the ground. We tried to get this in between the 2 drainage piles, so it'll be kind of uniform. We did that in 2017. I think we got like 3 weeks of data before a storm damaged all of our antennas and then broke the tower. Okay, so in 2018, we collected a longer set of data. We have some instrument issues that we were looking at resolving, so we still got a reasonably good set of data from there, but we're still working at reducing that. There we put 2 sets of soil moisture probes, one over the drainage tile and one in the middle. Okay, so based on these experiments, actually this shows what the antennas, these are all homemade antennas. And this shows what we had in 2017, and then these all got damaged by the wind. These are the S-band antennas. These are just commercial XM radio antennas. So I showed kind of some examples of what our raw data looks like. We do have a calibration network, so we are actually, in principle, reducing everything to SI units in our reflective power and our reflectivity. I think on later slides I'll show the more recent version of the front end, but we have some calibration loads like a radiometer would use. And this just shows, this is our actual cross correlation. I showed those illustrations earlier, but this is for P-band. We get this nice sharp peak at 0 delay. This stuff is interference between the direct and the reflective. The other interesting thing is S-band. We can see the flexing of the tower here. That was another effect we want to throw out. So this is when we do the calibration, but then this is when we're tracking the reflected signal. You see this fluctuation due to the power bending. Okay, so we did and we've only presented at conferences. I'm still looking at trying to clean this up to publish it, but there's some problems. But we've got a time series. Our first attempt at getting a reflectivity. This is the in situ soil. Yeah, this in situ soil moisture measurements. There wasn't a big change over our short time period before we get the tower got damaged. There was a rain event here. So it's all small amount of variation. So we put that into our forward model of the electromagnetic scattering, and then this just shows the plot of our reflectivity that we got from inverting our model. These are the two XM radio satellites, XM3 and XM4. Still got a lot of noise in it, but when we adjust the roughness and everything, we get at least the same order of magnitude, the generally the same trend as we're seeing from the the in situ data. So again, it shows the feasibility. But since then, during the pandemic actually gave us the opportunity to not be in the field for a couple of years, really go back. I got a student who really learn microwave design from fundamental principles to really go back and do this properly. So we have a new front end. Main thing is we have 4 calibration states. So we also have thermal control of the front end. So this is a CAD drawing, but we have this thermal control, maintain the constant temperature. This basically shows all the components of the front end. It's on a cold plate. We're hoping to resolve a lot of these problems we've had before. So this shows the newest configuration. We collected a little bit of data last year. It's still out there in the field. We're doing some testing now, and we're hoping to do. I've always each time, so I want to do like a whole growth season of something of corn. We're doing corn this year, and so I get really good data to show the change over the vegetation, everything. Hoping to finally get it this time. We have 3 frequencies now. Big configuration top of the tower. These are for 137 megahertz, and this is the L band of 1.5 gigahertz, and then S band also really tiny kind of there. Well, calibrated front end is on the tower. We'll have in situ data, and hopefully we can get some experimental validation of some of these algorithms. And I think that's the same image I had before that we showed our plan. And again, I talked to Brady about doing something the following year at Martell. We have a NASA proposal to continue measurements at the Martell Forest site. Okay, so that brings us to, in order to kind of make this a global measurement, we need to go to a satellite. So based upon those airborne experiments and so a limited amount of field experiments, we wrote a proposal to do a satellite demonstration, which we call Signals Opportunity P-band Investigation, or SNOOPI. This was written at Purdue. I'm the principal investigator. I don't build spaceflight hardware here. I have no desire to have gotten into that business. So I have a lot of colleagues at NASA Goddard and JPL. So the actual hardware was designed and built there. The digital section was built at Goddard. I'm sorry, digital section was built at JPL, the analog section, and the satellite itself was built at Goddard. I'll maybe skip over some of it. Oh, this did not turn out well. Okay, this should be a CAD drawing what the satellite looks like. It's all mixed up, but I have an actual picture of the hardware here. It's a 2x3 U CubeSat. This kind of shows a nice pictures of the time frame. The instrument was put together at Goddard sometime early 2022. I couldn't find the date on that one. We did our first live sky test. So this is outside in the parking lot at Goddard. Collected the signal, putting on this wooden stand, avoid any reflections. Then due to some bunch of stuff happening down here, and finally had it shipped to the company is going to launch it in the Aeronautics, and we're hoping to launch next month on SpaceX 30. And it'll go to space station and it'll be deployed from space station. So the mission plan, again, this is still a validation mission. So we're not proposing to produce any science product. We're just demonstrating it works. So our highest priority measurements are going to be matchups with the SNAP cow valve sites. So we had hoped to get, in our simulations, we showed we could get about 50 matchups with, over a 9-month mission, we get about 50, a little more than 50 matchups with the SNAP cow valve sites. We have an interest in looking at snow. That's more the JPL part. And then if we just look at over a month of data, these are the spectral point ground tracks across the continental U.S. The operations and the science processing is all going to take place at Purdue. We have something called the Science Operations Center, which is basically a piece of software. We don't physically have a room for that, but we like to say we have Operations Center here. So this is the software one of my research scientists developed, where we can select regions we want to collect data. This can plan a measurement. This shows just historic data for soil moisture, so trying to see what kind of variation we're going to get, and then put that timing into the operation. Since it is a tech demo, we only have about 5 minutes of data per day we can collect, so we're targeting these matchups of SNAP cow valve sites. In case you went to Acre, the other piece of equipment you may have seen out there that belongs to me is this signal monitor. One of my students came up with that background that called it wide ERP. And EIRP is effective isotropic radiated power. It's a common term in communication. But basically, this is to give us a measurement of the source. So we're going to look at the source transmitter, calibrated front end, look at the power, look at the spectrum, to kind of use this to inform our interpretation of the data. So and also do a sky survey to see what kind of background radiation we're seeing. So this was put together by Benjamin Knoll, who's this guy in the middle here, and he graduated and went to Goddard. So we're trying to finish it before the launch. Most of his thesis was simulating the SNOOPI measurement. I'll maybe skip through this and just show some of the results. So these are some of the simulations, and basically this is the signal to noise ratio of the measurement. So this kind of represents the how our ability to detect the measurement from the satellite. The DAF line is my theoretical model, and all the colors are different simulations that he ran with his his numerical model for like a Monte Carlo simulation. And we do simulations of the retrievals. I didn't include them in here. Yeah, this shows kind of the measurements we're making from the wide ERP instrument. Okay, so basing a whole mission on some simulations is something that's a little bit risky. So we did have the opportunity to do kind of a virtual satellite experiment in which this private company Spire operates a constellation of commercial satellites. They provide some remote sensing products to NASA and to I think to NGA, and they also provide some products like ship tracking and aircraft tracking, stuff like that. They had this one satellite that was used a software-defined radio that operated within this band that there's a transmitter. So it had reached the end of its life. From the customer, was done with it. So it had a few months left before it deorbited. So I talked to them, and we were able to reprogram this and try to capture that data and bring it to the ground, and then process it as we would SNOOPI measurements. We captured a minute of data. We were only able to download a little more than 9 seconds before it re-entered. So we got 9 seconds of data, but at least this proves, you know, the fundamental feasibility, I think. So I'm going to play this animation, and this is, you think of this as like a cross correlation, like when I showed the delayed aqua maps. This is at the direct signal, so I should always see a sharp peak at the direct signal, and then this is the reflected signal. So I have a lot, you know, I have noise, but then this is at the delay to the specular point, and I should see, you know, a peak there as well. I'm detecting both the direct signal and the reflected one. And as I go through these 9 seconds of data, we map this onto this area in north of here. I think this is in Minnesota, either Wisconsin or Minnesota. So a little bit north, all frozen ground. This is in the middle of December. So we're going to see as we track the specular point across the land, we're going to be able to see it. When we go to this little frozen lake, we're going to see a peak in power. We're going to see that this get much smaller in the background. And then somewhere over here, there's a short segment in which we believe see some interference. So I'll play this. So this as we're going to see, you know, we're tracking that specular point, and then soon it's going to get a peak. Get there, that's when we go over the lake, it'll get stronger, and then we go here and we'll see the interference shortly. Yep. Here, that little flash, that was the interference. Okay, so this at least shows me, you know, feasibility that we are actually going to be able to capture this method. Okay, so in conclusion, signals opportunity to make microwave measurements in bands that have not been usable for science in the past, because we're making use of non-cooperative transmitters that exist for other purposes that are using these very expensive spectrum licenses that they purchased, and we are just getting their radiation for free. We believe we can retrieve subsurface soil moisture and vegetation cover by appropriate combination of frequencies and polarizations. SNOOPI is going to be a technical feasibility study, and also, you know, produce a flight qualified receiver that could be used in future mission proposals. And we're beginning or continuing field experiments to try to validate these forward models and that's multi-frequency dual polarization retrieval algorithms. Okay, so thank you very much.
We do have time for questions. I want to get us started. So you may have just mentioned it in passing, but I'm wondering how you disentangle soil moisture measurements from above ground biomass or surface texture, those sorts of
Okay, well, I mean, all that stuff is basically going to a layered electromagnetic scattering model, right? So we have a model that, you know, basically represents here, it represents the vegetation for the part that we'll invert from measurements. This is a more sophisticated model which generates synthetic measurements, but we have, you know, right now we're modeling the vegetation as just a layer with a certain optical depth, right? Okay, and then we have scattering from different layers. So if I pick a given frequency, I'm going to see, you know, a given reflectivity that depends upon a bunch of parameters: the optical depth, soil moisture at different depths, etc. Okay, so one measurement, bunch of unknowns. So how do I solve for more unknowns? I make more measurements, right? So I need some independent measurements. So one way is to add different frequencies, right? So they're going to penetrate differently. They're going to have different responses to the vegetation. The other thing is to add two polarizations, because the vegetation responds differently to different polarizations, but soil is maybe more similar response. And that's basically what all these simulations I put together here show. My accuracy, as I increase my frequencies, my errors go down. As I add polarization, and I can look, the top one's single pole, bottom one's double pole. So if I look at vegetation, I think it's the black line. Black with triangles. These lines are just linear fit. So the black with the triangles, I see that adding polarization, I reduce my error in the BWC by almost a half. I go from there down to there. Okay, so basically more measurements, more frequencies, more polarizations.
Thanks so much for the interesting study. So, if, for example, if you're using the SNOOPI mission data to map the soil moisture in, for example, continental US, what would be the temporal and spatial resolution of that?
Okay, well, that'll depend upon, kind of what orbit we put in now. So again, I want to emphasize, SNOOPI is a tech demo, right? So we're making 50 feet. Our goal is to get 50 good matchups in continental US with, I think there was 9 SMAP sites. So we're not going to, we're not going to produce a science product from that. We're going to get, validation of, hopefully a nice scatter plot of these 50 points that show my theoretical prediction based on the measurements and the retrieves. Okay, now your question in terms of this coverage, and that comes down to, design of a mission. And, one of the advantages is since, this satellite is so small, right? You can launch a whole bunch of these in a constellation, right? So these are CubeSats. They're, about this big, 20 by 40 by 30 centimeters, okay? So you'll get up the coverage by launching a lot of them, right? So, I mean, it's feasible that we would get, daily coverage with, I'm going to take a guess, 10 satellites. I know one of the student who did those simulations, his second paper was on simulating the constellation. He's not done with that yet, but you'll get, with the reasonable number of satellites, you get daily coverage. So at much lower cost than say launching another SMAP. Okay, but again, that becomes a design issue. That becomes what type of constellation you want to put. Actually, it also depends on the number of sources too. So the one advantage of using GNSS is there's a lot of them there, and they're in a really good position to be seen. So if you, and nobody has an instrument that can do this yet, but if you had all 4 GNSS constellations, you have the GPS from the United States, Baidu from China, Galileo from EU, and GLONASS from Russia, you'll see 20 satellites anywhere on the surface of the Earth. So every measurement, you have these 20 spectral points scattered around. But if anyone has right now, I don't think anyone has a receiver that does that. But the data, the measurements are out there.
How long is SNOOPI supposed to be in orbit?
We propose 9 months. It'll probably stay in orbit longer than that. We're, we hope everything's reliable and it lasts for at least that long. But our proposal was, 50 measurements in 9 months.
Then what?
Then we're going to try to compete in the science mission. I know we talked, fire was one of the things we talked about. That's at least in the last go around, like this, the Roses Ball had a lot of stuff missing this time, but at least in the last go around, fire was a big thing, and there was talk about mission formulation team for a fire remote sensing mission. So that could be one option. Going through some of these commercial data buy concepts, like what Spire does, I'm in some discussions with companies that do that, so that's another possibility. Yeah, these are kind of the directions I'm looking at.
Other questions? Well, let's thank Jim one more time.
All right, thank you very much. Do I need to do anything here?